I'm going to be going over in this video the international M2 paper from Pearson's Edexcel, 21st of January 2015. Let's do the first question, pretty standard impulse question. We've got impulse is change in momentum, mv minus mu. So we want to find the magnitude of the impulse. We have everything we need here. We've got mass, we've got initial velocity, and we've got final velocity. So not a problem this. So we've got 0.6 v, which is 2I, which is a final velocity, plus 3j, minus this velocity here, which is 4I minus 2j. Work that out and we get minus 1.2i plus 3j. If we work that, don't forget we want the magnitude of the velocity of the impulse, so we can't leave it like that. It wants the magnitude of it, which is going to be the sum of all the squares of the components, ignoring minuses, because they don't matter because they just give a direction. That, if we break it down, is to three significant figures is 3.23. Okay, let's give three significant figures in our answers. They did in the mark scheme allow a third answer, but we'll leave it like that. So that is the first part done. The second part, to do with kinetic energy lost. Well, this is our initial velocity, this is our final velocity, so Ke lost is going to be half u squared minus half mv squared. Now you might be tempted to work out u and v here separately, say u is equal to the square root of 4 squared plus 2 squared, or whatever, but in fact we can just take the components of the weight, so that's a half times by 0.6 times by u, the components of u, that's 4 squared plus 2 squared. 4 squared plus 2 squared. Take away half of 0.6, 2 squared plus 3 squared. Okay, so that's a half times 0.6, the 4 squared plus 2 squared is 20, and the 2 squared plus the 3 squared is equal to 13. So that equals to 2.1 joules. Okay, and that is it for question 1. Nice easy question to get us into the paper. Let's see what question 2 has in store. Okay, question 2. So we've got a power and work energy principle question for the second part. Okay, so for the first part, we've got a car moving up a hill with angle phi to the horizontal, which is given. We know the angle. There's constant resistances. So we've got this car going up a hill. Resistances are constant, 150 newtons. There's obviously some driving force taking it up the hill, otherwise it wouldn't get up. And there's a weight of 500 g for the car acting downwards, and of course it's at an angle theta to the horizontal, and we know theta is sine theta is 1 over 20. So we can work out F just by applying F equals ma. It's at constant speed, that's the other important thing, 20 meters per second. That means that the forces are balanced. There's no resultant force causing acceleration. So the force upwards, F, is going to be equal to the component of the weight downwards, that's 500 g sine theta, plus 150. Let's change back to blue actually. Okay, so working that out, that's F is equal to 500 times 9.8, and sine theta is 1/20 plus 150. Okay, just to, that's going to be 50 times 9.8, that's going to 50 times 9.8. Right, and all that works out to 395 newtons, I think. Okay, so we're asked for the power, so P is equal to Fe is our power equation, and we know the velocity is 20, so we've got P is equal to 20 times 395, which is equal to 7.9 kilowatts, or 7.9 or 7,900 watts. Let's put it in watts. 7,900 watts, or 7.9 kilowatts, two significant figures. Okay, well, that's part A done, so that's quite a nice, easy, standard power question. Then it says, when the car is travelling up the road at 20 meters, the engine is switched off. The car then comes to instantaneous rest without braking, having moved a distance d meters up the road from the point where the engine was switched off. The resistances to the non-gravity motion is modelled as a constant force, 150 newtons. Okay, right, this is a work energy question, the work energy problem. The way I normally like to go about this is just to use a standard little equation which expresses the work energy principle. Any change, positive or negative, of kinetic energy plus any change, positive or negative, of potential energy is equal to work done positive or negative, because put work done against or work done by external force, which might also be negative. If it, and in this case it will be, because we'll have the resistances. Okay, so let's just do a little diagram. Let's put this on. Okay, we've got the 150 newtons here. Let's make d equal to the distance above here. Okay. This angle's theta, obviously, so this is d sine theta, which is d over 20, because we know sine theta is 1/20. Okay, so we're going to need that when we work out change in potential energy, which we're going to do in a moment. Let's call our zero potential energy here. Okay, what else are we told? The switched off, the car then comes to instantaneous rest, so we've got V is 0 up at this point, and we've got U as 20 here. Right, so let's just make sure we get our signs right. We're going to do final, take away, initial, so in each of these, final, take, initial in each of these, so that our signs is right. But we're also going to have a negative here because there's going to be work done by an external force. Okay, so let's fit this in, or let's go back to blue. So changing kinetic energy, that's the final kinetic energy, which is half times by 0.0 what was the mass of the thing? It wasn't half times 500. I had the 0.6 in my head from the previous question. The half times 500 times by 0 squared. Take away a half times 500 times by 20 squared. Let's move this across a bit actually. Okay, so that's the change in kinetic energy. It will have lost kinetic energy. It's obviously gained potential energy, which will be equal to this m, which is 500, times by g, which is 9.8, times by d sine 20, which is d over 20. Okay, because it's vertical height. Right, now that equals to the work done by the external force. Now this is key here. The work done by external force, it's not that someone's added, if the driving force was still that involved, then that would involve a positive because it would be increasing the total mechanical energy, as we say, kinetic energy and potential energy. But this force here is definitely is a resistive force, so it's taking mechanical energy away from the system. So that's going to be a minus 150 times by the distance. Work done is force times distance. So that equation is going to enable us to work out what we need. Let's work this out then. Okay, let's tidy this up a bit. The 20 squared that's going to be equal to 10,000. Okay, this amount of bits minus, of course. This amount here is going to be equal to 245 D is equal to minus 150 D. Okay, let's bring all that over to the same side. So we got that as equal to 395 D is equal to 10,000. Now divide that through. We get that as 253, but I'm going to give it to two significant figures. So that's 250 meters. They did accept for it. They do accept 3 significant figures, but nothing else here. I'm giving it to 2 because we use G in our answer. In our question. Okay, so we're 13 minutes in. We've done the first 2 questions, so not going too badly so far. Let's see what question 3's got in store. Okay, so it's motion in 2D, a little bit different. It's got some lambdas in it, but I'm sure it'll be fine. Normally not too bad, these questions. So we've got R equals to, let's just write in the question out here, minus 2 lambda t squared plus 5I plus 5t squared minus lambda t j. Now it's talk about it moving parallel to p when t equals 4 to j. So that means it's moving in that direction or in that direction, up or down. And the key thing is I is going to be equal to 0 because there's going to be no I component because it's moving, basically it's moving in a vertical direction. So let's differentiate to get our v. That's going to be 1/8 t to the 4 is going to be a half t cubed minus 4 lambda t I plus 10t minus lambda j. Right, now it tells us that when t is equal to 4, it's moving parallel to j. So that gives us, when t equals to 4, I component equal to 0, because it's moving only in a vertical direction. So we have a half times 4 cubed minus 4 lambda times 4 equals 0. This is one of these nice situations where they tell you the answer. This bit is 32 minus 16 lambda, which is equal to 0. So that gives us lambda equals 2 as required. Nice. Okay. Then it says find the speed when t equals 4. Well, we know, so we can put t equals to 4 back into this. We've now got v is equal to a half t cubed minus 8t, because we now know that lambda is 2i, plus 10t minus 2j. Make my j look a bit more like a j. That's better. Okay, so when t equals to 4, we have v is equal to a half times 4 cubed minus 8 times 4. Well, actually, we know that's 0, so that's a bit of a waste of time. We knew, never mind. Sometimes that happens. I've just done that. I'm feeling a bit silly, really, because I should have known that this was 0i, because it's told me already that the speed is equal to that it's moving parallel. So I'm feeling a bit silly, but I'm not going to go back on it. Now we put t equals to 4 in here. That's 38j. Right, so the speed is 38. I'm feeling daft now. Never mind. Don't need to use Pythagoras here. Results, I was expecting it. It just shows you sometimes you can turn a handle, and we could see that the speed was 0 here. So a little bit unnecessary. All I really needed to do, which is why there was only 1 mark for it, was put 4 into there. Shame on me. Never mind. Okay. Part C. Find the acceleration of p when t equals to 4. Well, I've got to accelerate. I've got to differentiate this again. That gives me the acceleration is equal to 3 over 2 t squared minus 8 I plus 10 j. So when t equals to 4, I have acceleration is equal to 3 over 2 times 4 squared minus 8 I plus 10 j. So that gives me that's 16I plus 10j. Doesn't ask for a magnitude here. It says find the acceleration. So I don't need to do this thing. I don't need to work out this, because it asks for the acceleration, not the magnitude of the acceleration. So part D. When t equals to 0, p is at the point A. When t equals to 4, p is at the point B. So we're going to have to work out. We've got our position vector now with lambda that we know. So when t equals to 0, r equals to 5i, and that's it, isn't it? Because the j bit goes, putting it into here, knowing that lambda equals to 2. And then when t equals to 4, we have r equals 1/8 of 4 to the power of 4 minus 4, because lambda was 2, remember, times 4 squared, plus 5, and that's all times I, plus the j bit is 5 times 4 squared minus 2 times 4 j. Okay, that actually breaks down to this first bit here equals to 27i minus 27i, and this bit here, that's going to be 80 minus 8, which is plus 72j. Okay, so we have the position vector, our two position vectors that we need. Okay, so the distance is going to be the magnitude of the difference between these. If you think about it, this is at 0.5 and this is down, and we're just finding the distance between them in that direction. So we're basically using Pythagoras. The difference between the I components is 32, that's squared. The difference between the j components is 72, that's squared, square root of that, and that equals to 78.8 meters. It definitely gives pretty significant figures now because there's no g, so g 2 may well not be accepted. I don't think it was in this scheme. Okay, so 22 minutes, third question done. Let's see what question 4 is like. So it's centre of mass, not always the easiest of questions, and I don't think this is the easiest of questions either. I remember my class doing this as a mock last year, and most of them split this up into each one of them. They used symmetry across the line here, so they knew the centre of mass was going along here. It's implied in the question anyway. And they started fiddling around with half angles here, using the fact that the centre of mass is in the middle of those. Actually fine, but a slightly longer way of doing it. The way I'm going to do it here is actually how the mark scheme implies as well, is the centre of mass will be halfway along this line, won't it? Because we can see that it would be halfway along there if we move that point across. That makes sense. So the centre of mass would be there, halfway up the rhombus along the diagonal, produced across to the line of symmetry between the two, because of course we've got the same thing going on the other side there. So the centre of mass is there. Now, if we look at this triangle here, okay, this length here we can work out relatively easily without too much of a problem. So because it will be equal to, let's mark some angles on first. There's a lot going on here. This angle here is theta, because let's just rub this out for a moment. This angle here is theta, so we can see those two angles are the same. Okay, so we want to work out this length here, which is A, plus this length here. Now this length here is clearly A cos theta. Okay, the length here is A. So the centre of mass will be halfway along that. So centre of mass, which we're told is 0.9a, is going to be halfway up the length from here to here. So that gives us 0.9a equals to a half of this total length here, which is a plus a cos theta. Okay, just repeat again because it may not have been the easiest to see. Judging on my group last year, it certainly wasn't the easiest thing to see. It was the fact that the centre of mass is going to be halfway along here. So the centre of mass is going to be halfway along this line here, which we can work out the total length of that there because it's a plus a cos theta. That's the most efficient way of doing this question. Other ways are possible. Most of them involve half angles, fiddling about, but I think that's the nicest way. So that's 1.8a is equal to a plus a cos theta. Obviously a cancels, so cos theta is equal to 0.8 as required. They've allowed 5 marks for the question, so if we have used half angles and all the rest of it, hopefully it still has been worth it. And the mark scheme does allow for those different variations, but that's the nicest way of doing it. Okay, so I'm going to rub out all those annotations now and then do part B. Part B talks about, well, we now know that the total mass of the thing is the total weight of it is W, and we're told that a weight of kW is suspended from A. So it's not suspended, it's placed at A, and it's freely suspended from B. Okay, and that DA is horizontal. So this is horizontal here, which must mean our vertical line, a line going downwards vertical, is here. So I've kind of rotated the diagram without having to redraw. So that must mean that our centre of mass is here. Okay, centre of mass is there. Because the vertical line has to pass through the centre of mass of the system. So what we need is this distance here and this distance here. Well, this distance here is pretty easy. That is going to be equal to just a cos theta. But this distance here is, well, we know that the distance of the centre of mass from here to here is 0.9. So that gives us 0.9 a minus a cos theta, is that small distance between the centre of mass of the shape without the kW and the vertical line. So that means that this, we can now set up our moments equation, taking moments. We can say that kW times by the distance here that we've worked out, which is a cos theta, equals to W times this small distance that we've worked out here, which is 0.9a minus a cos W. Well, minus a cos theta. I'm saying half the time. Okay, so if we work that out, W obviously cancels, A obviously cancels, so W and A cancels. We know cos theta is 0.8, but I'll not bother putting it in just for the moment. That gives us, go back to blue, K cos theta is equal to 0.9 minus cos theta, Let's put it in now. So 0.8k is equal to 0.1. So k must be equal to 1 over 8. Okay, now it hasn't taken that long to do that question, but I suspect if we'd got bogged down with double angles and things, it would have taken longer. And like a lot of things, if you pick the most efficient method from start off, it's always going to be quicker than if you have to fiddle around and get your head around it. It's not the easiest of centres of maths question, really. Okay, I think we'll do the next part, the next few questions, that's 5, 6, 7, in a separate part. Okay, coming soon.